Hello, my name is Kevin Sigwart. I'm a principal consultant at One Spatial. During this video, we will be demonstrating how the One Spatial commercial off-the-shelf tools can help with the cleaning and conflating of extracted features from Rasters, Imagery, and LIDAR datasets. There are many excellent third-party feature extraction tools that can identify and extract vector features from raster imagery. However, the extracted vector datasets should go through proper quality assurance and quality control, and will likely require a bunch of cleanup work. Once the data has been cleaned, it will then need to be integrated into an existing Geographic Information System, or GIS. We will be demonstrating how using the One Integrate tools can automate the process of validating the extracted features, cleaning the data using generalization and smoothing algorithms, and then integrating the data into an existing GIS. At One Spatial, we define three aspects for having the spatial advantage: data validation, data enhancement, and data integration. The One Integrate product has a rules engine that can automate the validation of geospatial and non-geospatial datasets. This reduces the time-consuming and subjectivity when doing a manual quality assurance task. In respects to feature extraction, rules can be written to ensure that extracted features are of a certain size, do not self-intersect, have gaps and other topological issues, or even in the case of LIDAR extraction, making sure that height attributes extracted conform to existing datasets. Once the One Integrate product has identified the nonconformances, actions can be written to identify how to correct the data. This can automate the cleaning of the datasets, whether that is fixing the topological issues, edge matching across the boundaries of two adjacent raster datasets, or smoothing and generalizing the extracted features. After the data has met the quality control standard identified in the rules engine, the data can be integrated back into an existing GIS system. This can be updating the attribution. For example, updating your building footprint attribute so that the height field matches the height of the extracted building from LIDAR data. The One Integrate can also align the extracted data with existing surveyed geospatial data. Lastly, if you already have an attribute-rich but low-resolution dataset, One Integrate can conflate those attributes over to a high-resolution extracted feature dataset, resulting in an attribute-rich, high-resolution dataset. We will be doing 4 demonstrations using our One Integrate product on extracted features. The first demonstration is working with a plot paper map that was scanned, georeferenced, and extracted and needs to be aligned with existing parcel data. The second demonstration is working with cleaning contours that were generated from a digital elevation model, or DEM. The third demonstration is working with LIDAR extracted buildings. And the fourth demonstration is showing how we can conflate the NHD reach codes from the NHD data over to a high-resolution LIDAR-generated stream dataset. For this demonstration, we have a paper map that was scanned, georeferenced, and extracted. The extracted features did not align with the parcel data, leaving many gaps and overlaps. The One Integrate for ArcGIS technology can identify where those gaps and overlaps exist and then align the extracted features with the underlying parcel datasets. Let's go ahead and take a look. Alright, so we're currently going to be using ArcGIS Pro and the One Integrate for ArcGIS toolset in order to help us validate and correct these extracted features. Now we're using ArcGIS Pro, but we could also be using ArcMap, or if we're using the One Integrate for ArcGIS Server Edition, we could be also using this through a web browser or even on a mobile device. So what we have here is we have this map plot, and what we want to do is we're going to be using some third-party software to extract out the features inside this area over here, which you're looking at. So I'm going to go ahead and zoom to that particular area. And when we use that third-party software, we extract out the data set. Now, if I take a look at this data set, we're going to notice some issues with the data. For example, it's not exactly straight lines. It has lots of extra vertices and sorts of issues like that. Not only that, is that I need to align it with my current parcel data. So when we look at my parcel data, we can see that we have areas where it's not filled in. We have places even where it's overshooting. So what I'm going to do is I'm going to use the One Integrate for ArcGIS toolset to find where these issues are occurring and then align the data to actually match up with the parcel data. So we're going to go over to my One Integrate for ArcGIS widget. I'm going to switch over to my Enhancement tab, and we're going to go ahead and run my rules and actions to fix this data. Once this is finished, you'll notice that we now are completely aligned with the parcel data. And this is all being done with inside an edit session in the Esri environment. So when I click on my edit tab, at any point I can either save those edits back to the underlying data set, or we can disregard those edits and it goes back to the way that it was. For the second demonstration, we're going to be working with contour data. We were given 687 1-meter resolution digital elevation models, or DEMs, that were generated from LIDAR data. We used Esri's ArcGIS tools with Spatial Analyst to generate the contours. Once those contours were generated, we noticed issues with having self-intersecting lines, the contours having jagged edges, lots of extra vertices, small contour polygons, and gaps in the contour line between two adjacent DEMs. We then used One Integrate to identify where those issues were occurring and then build actions to clean the data. Let's swing back to ArcGIS Pro and look at some of these contour data. Alright, so we are now in ArcGIS Pro, and we are going to use One Integrate for ArcGIS again to help us validate and clean up the generated contours. But before we actually start looking at the generated contours, let's show you how we actually generated them. So what you're looking at here are the 687 footprints of the contour data. If I zoom into a particular location, we will see the digital elevation model that was generated. And as I pan and zoom around the map, we can see this across all these footprints. So as I said earlier, we use the Esri technology, the Spatial Analyst, to generate the contours. So when I turn on my contours, we should see them showing up in the map. And you can see that we have these contours. What you'll notice is that they look pretty jagged, and it looks like there's a lot of, let's turn off this, there's a lot of small polygons being created. So what we're going to do is we're going to run some validation checks to validate my data. So I'm going to go ahead and pan out, and we're going to run some rules on this extent here. So I'm going to switch over to my One Integrate for ArcGIS tab. I'm going to open up my first set of validation checks, and we're going to go ahead and run it. So the first set of validation checks I'm going to do are my essential geometry checks. These are the checks that come out of the box with One Integrate for ArcGIS. They check for things that happen when you're doing data editing or doing feature extraction. They check for places where you have two features that are the exact same, places where you have multiple vertices showing up at the exact same location, kickbacks and spikes. These are kinks in the data. We're also checking for self-intersections where the feature intersects itself. Now you'll notice this happens a lot inside of doing feature extraction. Now what we did is we processed through 8,366 contours. These contours, as you saw before, are pretty complex. They have lots of vertices, and we were still able to do the validation in under a minute. And it was 8 validation checks in that short amount of time. And this is because we use an object-oriented cache to do the data validation. So we extract the data out into our cache. It is an object-oriented database designed to do these quick validation checks across multiple features. That way, that's the reason why we can do so many validations so quickly. Now if we look at the map, we're reporting on how well we map to each individual rule. If I come back over to my widget, for each one of these rules, we give it a green, yellow, red status based off of how well our data conforms to the rule. For example, for duplicate features, we have a green. That means there's 0 nonconformances across all my contours. Where it's yellow or orange, that is where we have some issues. So for example, I have 334 self-intersections. Now when I look at the map, I can actually pinpoint where all these are occurring. And if I come back over to my Contents tab, we have 3 layers that are notifying us where we have issues. I'm just going to look at my self-intersections, and we can pinpoint where these are actually located. If I want to share this with another individual that is maybe the editor, I'm just a QA/QC person, I could right-click on the layer, go to data, and export those features out and send them a shapefile or a file geodatabase of where these issues are occurring. So I'm going to just go ahead and zoom over to a particular area. And we could see here we have a notification that there's a self-intersection. When I zoom into that self-intersection and I select my line, you can see that this guy intersects itself. And this is occurring throughout the entire data set. And we can zoom into another area just to take a look. And we can find another place where we have a self-intersection. The next set of rules I'd like to run are more of a custom set of rules that are more specific to doing contour validation. In this, we're checking for where do we have contours that are too small. So if the contour is closed, we check the area of that closed contour to see if it is less than a certain value. For example, less than 150 square meters. We also check to make sure that 2 contours don't cross each other. They shouldn't be intersecting each other or crossing each other. Now we just ran that, and we could take a look at where we have these particular issues. So I'm going to go back and zoom to that same area I was at before. And we can see where we're notifying us that there's small polygons. So for example, this guy here is giving us a notification. If I come to my measure tool and measure an area, and let's go ahead and measure my area. It is only 14 square, oh, sorry, there we go. It is only 10 square feet, right? We have that our tolerance is 150 square meters, so this is obviously way, way too small for our rule. We can also see where we have contours that are touching. So I'm going to come back over here and I'll just go to one of these examples. And we can see here we have 2 contours that are touching. So I have this contour and this contour. Right? So this is an issue that needs to be fixed. Let's switch over to our rule authoring environment where I can show you what these rules actually look like and how you can write these rules. Alright, we are now inside the Integrate for ArcGIS rule authoring environment. For this particular rule, we're checking to make sure that 2 contours do not cross. So how the rule is written is we take our contour, we loop through each individual contour, and we make sure that there is exactly 0 other contours where the geometries intersect. And when we do this not equal to, that's making sure that it's any other contour. Now, as I said before, this is a fully interactive rule authoring environment. We can change and add additional rules if we so desire. So for example, we can make sure that not only do they intersect, but they don't intersect and they have the same value. So we can come in here and add an additional check. In this case, we're going to say the attribute value, my contour value, should be equal to the attribute value of this contour value. And you can build on this as you see fit. Another example rule is where we're checking the contour area. So let's switch over to that particular rule. Alright, so for this particular rule, we're looking at all of my contours. We're first checking to make sure that that contour is actually closed, because if we want to calculate the area of the contour, it must be a closed contour. Once we know that that contour is closed, we can then make sure first the contour is greater than 0, the area of the contour is greater than 0, and notice how we're building functions on top of the geometry. So you can nest functions on geometric values, numeric values, or even string values. So we convert that geometry to a polygon and then calculate the area. And then we also make sure that the area is greater than 150 square meters. Now, as I said before, this is interactive, so maybe we feel that 150 square meters is too large and we want to change that value. So we come in here, change the value to 50, save my results, and then republish this so it's now available inside of my rules engine. Alright, so switching back to ArcGIS Pro, the last time I ran this rule check for the small contour areas, we had 437 non-conformances. But you just saw we just updated and published that rule so that instead of a 150 square meter check, we changed it to a 50 square meter check. So let's go ahead and rerun the rule and see if we got any changes in this. So now that this has finished, we can see we went from 437 nonconformances all the way down to a whopping 405 nonconformances. It wasn't a huge change, but you can see that we have narrowed down the rule so that it knocked out about 30 or 32 nonconformances. So we were able to find where these issues are occurring, but the next thing we want to do is actually correct those issues. So I'm going to switch over to my enhancement tab and I'm going to zoom to another particular area. And let's go ahead and turn off that. So here we have my contours. When I zoom into the boundary, we'll notice that not only do we have issues with self-intersections and jagged features, they're not actually connecting. So what I'm going to do is I'm going to write some rules to actually fix my data. So we're going to go switch over to my One Integrate tab. The first thing I'm going to do is smooth my contours, to remove excess vertices and to smooth it out after I remove those excess vertices. After running this, we could take a look at the results. So I'm going to zoom in and we could turn on what the data looked like originally, and we could see how we actually smoothed it. Now you'll notice that we're doing some pretty heavy smoothing. This is fully tweakable, so we can change how much generalization we're actually going to do on that particular feature. And actually, even in the case of when we're doing work for NOAA for maritime data, we actually not only did we generalize the contours, but we made sure when we generalized that we stayed on the deep side so that we weren't going to create a navigational hazard. So these things are all possible within the rules engine. So let's go ahead and zoom back out. After we smooth my area, the next thing I want to do is remove my small polygons. So we're going to go ahead and now run this. It's going to remove all those polygons that are less than 150 square meters. So if I zoom back to that particular location and I turn on what it looked like originally, you could see that we removed all of these features. Something else that's important to note is that not only did we, when we generalized it, we also got rid of the self-intersection. Now that we have all those excess feature is removed, we then can edge match my contours. So we're going to find any contour that has the same value that's within a certain tolerance of each other, and then we're going to connect them. So when I come now and zoom in to my contour, we should see now that it's connected. Now how we decide on how we connect these can be up to the rules that we define. But in this case, we just drew a straight line between the two. And we can see that this is occurring throughout our entire data set. So I can go ahead and take a look at what it looked like before and after. And we can see this all the way across here. The third demonstration will be working with building data that has been extracted from LIDAR data. The building footprints and rooftops were extracted from the LIDAR data, and each polygon was populated with a min and max height. We are going to use OneIntegrate to validate the geometries and attribution. Before diving into OneIntegrate, let's take a look at the actual data. Alright, so we have two data sets that were generated from doing the feature extraction. We have my building perimeter, or my building footprints, and my building rooftops. So let's take a look at this building perimeter right here. And we can do a identify on that building perimeter. And for this building perimeter, notice that we have some attribution, but the attributes I want to focus on right now are my min and my max height. So because we're using LIDAR, we can actually extract out what the height and the base of the building is actually at. If I take a look at my building itself, the building rooftop, and select one of these building rooftop polygons, we have attribution also for the min and the max height. Now what we want to check, one of the rules we're going to run is we're going to make sure that if this building is within this footprint, the range of values of the min and max height should be within the range of this particular, the footprint's min and max height. So since this min and max height is from 25 to 38, we should make sure that the rooftop itself is within that particular range. So that's an attribution check we're going to do. We're also going to do geometry checks. We're going to make sure that the building rooftop is within a certain percentage of the building perimeter, because we know that a rooftop may extend slightly over the edge of a building when you're, especially when you're dealing with real buildings, they may extend over a little bit. But we're also going to make sure that if we have a building perimeter, it should have a rooftop. So in this case, we have a couple polygons right here where there is no rooftop. And we're also going to make sure that we have proper topology so we don't have gaps like the gap that's right there. So what we're going to do is we're going to shift over to our OneIntegrate product, and I'm going to show you how you can write these rules to do this validation on these data sets. Alright, so now we are looking at the OneIntegrate product. The OneIntegrate product is a server-based solution where you can connect into your data sources, validate it, and correct it all through this server-based product. So there's four main components of the OneIntegrate product. There's your data store where you connect to your data sources, the rules where you run the validation checks across the data sets, the actions where you do corrections to the data, and you have your sessions where you actually run through the set of rules. So let's go ahead and switch to our data store. And in this case, we're connecting to two shapefiles, my building perimeters and my buildings. And if I look at that data set, this is a shapefile. We can connect also to file geodatabases, enterprise geodatabases, or even native spatial types like SQL Server, Oracle, and Postgres. Once we bring that data set in, we have access to the entire schema of the data set. So the name of the feature class and all of the attributes. Then we have our rules where we can run our rules against this particular data. So for example, I can take a look at one of my rules, and we have actions and then the session. The session is where we run it. So I'm going to fire off this session and then I'll walk you through what we're actually looking at. So let's fire off the session. We are opening up the data sets, then we're running through our rules. So we're making sure that the building perimeter or the building footprint fully contains at least one building. Notice here that when we ran through this rule here, we only have a 22% conformance. If I open up this rule, I can look at the results inside of a map viewer, and I can see why this is the case. So let's go over to my report tab and look at this. So when I look at this particular building footprint, it's telling me that there's not at least one building rooftop that is contained within this building. So when we look at this, we could see, oh, this guy definitely is not within it. This top is not. This one isn't. So we can definitely see that we don't have all of our building rooftops contained within this building. That's why we're only getting that 20% nonconformance. And if you think about it, it's not a really good check to see if the building is completely contained within the footprint, because a building rooftop may extend outside that range. So what we're going to do is we're going to update our rules, but let's actually show you this rule before we do that. So if we take a look at this rule, we're saying that for my building perimeter, there's at least one building where the geometry is completely contained within that building perimeter, or they completely cover each other. So we go back to my session. The next thing we're going to check, we're going to update the rule a little bit. And let's take a look at that particular rule. And in this case, we're saying that for every building perimeter, there should be one building that intersects the building, and the intersection is 50%. So 50% of the building is contained within it. When I come back over to my session, we could see that we have a 55% conformance now with that particular check. The next thing we're checking for are that the building perimeters do not overlap other building perimeters. So you don't have overlapping building perimeters. We can take a quick look at this rule. And we're making sure that if we have these two building perimeters, they don't actually overlap. We can check to see, we can check those address ranges. So let's go ahead and check those address ranges. And now we're looking at, for every building, we're looking at the building footprints where they intersect, and they make up 50% of that intersection. We're saying that the min height must be in the range, and the max height must be in the range of the building perimeter. And then what we do next is, instead of just having this interface to view the rules, we're going to write out the results to what we call markups, so we can open those back up in our GIS editor of choice to look at the results. So this is where we're writing out where there's gaps, or writing out where there's overlaps, and where the buildings do not intersect other building perimeters. So let's go ahead and go back to ArcMap and show you those results. Okay, so we are back in ArcMap, and I have my markups where I exported it out of OneIntegrate, and this is where we can identify where we have gaps and where we have a building perimeter that has no buildings. So we can see everywhere where there's these blue polygons, that's where there's no building within the building perimeter, and then places where we have the red or where there's gaps. And I can zoom in and take a look at all these different gaps throughout the map itself. So using OneIntegrate, we were able to identify where we have issues when we did the feature extraction. The next demonstration we're going to switch to next is going to do with what do we do with it now that we have a clean data set that we extracted from our LIDAR data. The final demonstration is where we are taking a high-resolution LIDAR-generated hydrology dataset and conflating the attributes from our USGS National Hydrography Dataset, or NHD, over to that high resolution LIDAR data. We have rich metadata already within our NHD data, and we do not want to lose all that information when switching over to a higher resolution dataset. So we can use OneIntegrate to identify which NHD feature matches the high-res dataset and then conflate the reach code from the NHD dataset to the LIDAR-generated dataset. Alright, so before going into OneIntegrate to do the conflation, let's show you what we're dealing with. Right here in this map, we have the NHD dataset. And what I also have is I have the LIDAR enhanced or the LIDAR created dataset. So I'm going to go ahead and turn this guy on, and we can see that it is much higher resolution. Let's go zoom into a particular area, and we can see that it is indeed a lot more higher resolution. And if I look at one particular area over here, we can take a look at the attribution itself. So I'm going to grab first my NHD data, and in my NHD we have the name of the data set, and we have a reach code associated with it. But if I look at my flow line data or my LIDAR data, you'll notice that none of this is populated. So what I want to do is I want to find out where do I have my NHD data, where there's a matching LIDAR data set, and conflate over those attribution. And to do that, we're going to try to find any stream that's within a specific tolerance and that has the same bearing. But then after we do the conflation, we're going to go back and check through to see if there's any issues with the conflation that we did, so if we need to have any sort of manual intervention once the conflation has actually occurred. Alright, so let's switch back to OneIntegrate, and within OneIntegrate we are going to do our conflation. So I'm in my session queue right now. I'm going to go ahead and run my session queue. And what's happening inside the session queue is we're opening up our data sets. So we're making sure that we have our high resolution LIDAR created data set and the original NHD data set. Once we have that data, we're going to do some pre-processing to clean the data up, because we want to make sure the data is in the proper state before doing the conflation. The next step is to find the matches. Find where our low resolution feature is matching the high resolution feature, because in order to do the conflation, we got to find which features match. And to determine the match, we are looking at a specific tolerance of the feature. So we're looking for a 20-meter buffer, and we're checking to see if these two features that intersect are moving at the same bearing. Once we have our matches, we then build our proposals. And for our proposals, we're going to attach a confidence ratio based off of how confident we are in the actual match. And to do this, we determine how much of the features do they actually match, and so forth. Once we have all of our proposals, we're then going to remove proposals that are not within our specific tolerance. Lastly, we're going to actually bring over and conflate the features over to our high resolution data set. Then we're going to go back and we're going to check how well we actually did the conflation process. We're going to look for issues within that conflation. For example, we're going to make sure we don't have a bifurcation. A bifurcation is where you have three features with the same reach code all meeting at the same vertice. We're also going to make sure we don't have a gap in our reach code. So if there's two features that have the same reach code but they're not connecting, then we know that there's a gap in the reach code. So now that we've run this, let me just quickly show you an example of the conflation process. So I'm going to go over and look at the matches. Inside my matches, we have two sets of matching going on. We have our flow lines and our water bodies. We'll take a quick look at the flow line. And I have my source NHD flow line and my high resolution NHD flow line. We're buffering the geometry of my flow line by 20 meters. We're going to intersect our geometries. Then we're going to find the bearing, making sure the bearing is within a specific tolerance. We're going to create our confidence. Our confidence is based off of how much these intersecting geometries are equal to each other in length. And then we build out that match. Now that we've finished running through this session, I can show you the actual results. So let's go switch back to ArcMap and show you those results. Alright, so now we're back inside of ArcMap, and I'm going to go ahead and turn off this original LIDAR data set and turn on my result data set. So this is the LIDAR enhanced data with the conflated attributes. And to take a look at that, we'll go and zoom to one of those examples here. And I'm going to zoom in. And we can do an identify now on that feature. And we can see that this is my source data set, and my LIDAR enhanced data set now has the river name, and it also has my reach code. Now when we built out this conflated data set, we first did a set of proposals. Those proposals have whether or not we have matches, creations, deletes, and so forth. So you'll notice wherever we have a flow line in the LIDAR enhanced data set where we don't have a matching NHD data set, that is a create or an add. We also have examples of places where there were deletes. So here, if we take a look, we have our original data source, and we have my LIDAR data set, and we'll see that this guy is no longer here, and it actually is a stream that goes along here. So this is marked as a delete. So those reach codes will have to be deactivated. Now when we're doing this conflation effort, we're also going to check to see how well we actually conflated the attributes. Do we have any issues? And that's where we are checking for where we have branches in our reach codes and gaps. So I can turn on this data set and find where we have these issues at. And if I go back to my bookmark, we have some bookmarks. So if I go to branch 1, we'll see here we have this guy here, and if I select my 3 features, they all have that same reach code. Because we have 3 features meeting with the same reach code, we know we have some sort of bifurcation or a branch. And these guys should not have the same reach code, because you can't do network routing with the streams if they all have, if you have 3 features meeting with the same reach code. So what probably happened here is that this guy, if I select him, he has that reach code of 1008. Both of these features are within specific tolerance, and they both have a bearing, the same bearing, which is why we're getting those 2 features being conflated. So we have 2 options. We can flag it and have manual intervention to go in and fix it, or we can even enhance our rule a little bit to ignore when you have a smaller feature versus this longer feature. The next example I'd like to show is where we have gaps. And I'm going to see right here, we're identifying as a gap, and there's a gap right here, and we'll zoom to that particular location. And if I look at my flow line, we'll see, and let me turn off this, and we'll take a look at all my reach codes. So here we have a reach code of 1236. Also, this guy is 1236, and this guy is also going to be 1236. But if we look at this particular segment, we'll notice that it doesn't have that reach code. And the reason why it doesn't have that reach code is that because it is outside of the tolerance, right? So we weren't able to conflate it over. So this is where another place where there needs to be some sort of manual intervention to check to see why this is a gap. Now there are other examples where there's gaps where it's an actual physical gap. In this example, we take a look. we're going to find that the gap is actually not because of a problem with the conflation. It was actually because the LIDAR data actually showed that these streams are connecting. So we take a look at the original data, and then I turn on my LIDAR data. You'll notice that there is indeed a gap, and that is because these are not actually supposed to be connected at all. So at some point we had to retire the reach code and regenerate our reach codes for this particular feature. So that was just a quick overview of how we can use OneIntegrate to conflate over a attribute-rich, low-resolution data set to a geometrically rich, high-resolution, LIDAR-created data set. Throughout the video, we showed 4 examples of how you can take extracted feature data and give it the spatial advantage through data validation, data enhancement, and data integration using the OneIntegrate product suite. If you have any questions with any of the content shown in this video, please reach out to me at kevin.sigwart@onespatial.com or contact us at our website at onespatial.com.